Welcome back. This is the third and final lesson for this chapter. We left off talking about precipitation reactions, and we're going to talk a little bit more about chemical reactions like precipitation reactions and what they mean. Well, at least about more information about them. So this reaction up here is a precipitation reaction. Lead nitrate, aqueous. Aqueous means it's dissolved in water. Plus 2 potassium chlorides. Aqueous makes lead chloride solid plus 2 potassium nitrates. Okay, so this is known as a molecular equation because we've mixed everything together in its molecular form. So when I look at this equation, I think, okay, I've taken lead nitrate, I've put it into a beaker of water. I've taken potassium chloride solid and put it in a beaker with water. And then I mix the two together. And now I have lead chloride on the bottom, and I have a dissolved solution of potassium nitrate on the top. So this way I see that. And then, but what does the top equation mean? So lead nitrate, it's not sticking together as lead nitrate. It breaks apart into lead plus 2 ions and 2 nitrate anions, and then 2 potassium ions and 2 chloride anions, and it yields lead chloride, and there are 2 potassium ions and 2 nitrate anions. So this is known as the total ionic equation, or complete ionic equation. Now if you notice something, nitrate and potassium are on both sides of the equation. So what we name that is they're spectator ions. Like if you're at a baseball game and you're sitting down eating peanuts, you're a spectator. You're not on the field. You're not running the bases. You're not up to bat. You're not catching balls in the outfield. Okay, you're a spectator. You're watching the other people do the work. Then the complete ionic equation, the net ionic equation is here. This gets rid of all the spectator ions. So lead plus 2 plus chloride, both aqueous, make lead chloride solid. So this is sort of like the Cliff's Notes. I don't know if I'm showing my age here, but if I didn't want to read a book, I could get the Cliff's Notes. They would give me the synopsis. So like Grapes of Wrath. The Jodes left for California. They get there. They're still poor. And it ends with a curious smile. That's the Grapes of Wrath for you folks, right? So that's the quick and dirty story. This is the quick and dirty story with a chemical reaction. It's the net ionic equation. And we're going to talk a little bit about acids and bases, not too much, much more in the second semester. But acids, when you're thrown in water, they form what's known as the hydronium ion. That's H3O+. Bases form hydroxide in water. That comes more important later. You can also have polyprotic, so that means more than one proton, more than one hydronium from that. So sulfuric acid, H2SO4, is an example of a polyprotic. So some common acids and bases here. So hydrochloric acid, hydrobromic, hydroiodic, nitric, sulfuric, perchloric, those are strong acids. And acetic acid and hydrofluoric acid, those are both weak acids. Strong acids are strong electrolytes. Weak acids are weak electrolytes. We talked about that last lesson. So then we have the strong bases here. Although calcium hydroxide is not very soluble, it wouldn't make a very strong electrolyte. You can drink the stuff, and it can soothe your stomach. I don't think it's. Anyways, the book says it's so. We'll say it's so. Sodium hydroxide, lithium, potassium hydroxide, those are all extremely soluble. You do not want to drink those. Calcium hydroxide, you actually can drink that. That's okay. Barium hydroxide, you don't want to drink it. So you may argue that it's still not very soluble, though. But strong bases, sure, strong bases. Ammonia, that's a weak base, so that will definitely be a weak electrolyte. So, all right, how do we write equations for acid-base reactions? You have the acid plus the base makes water and a salt. And we talked about that last chapter, that salt is the result of an acid-base neutralization reaction, one of the definitions. And if you have a molecular equation, You the molecular equation, so 2 hydrogen iodides plus barium hydroxide makes 2 waters and barium iodide, aqueous. And the net ionic equation, you can the barium is soluble in both, and that's nice. The net ionic equation for for acid-base neutralization is just hydrogen. Well, we use hydrogen and hydronium interchangeably. We'll talk a little more on that next semester, but they can be used interchangeably. And then, so really, what you're forming in acid-base neutralization reactions is you're making water. Okay, so an acid-base titration. So the idea behind titration is a way of figuring out how much stuff is in stuff. Titrations are still used today. Do them very frequently. How much stuff is in stuff? We have machines that do it for us in a much more rapid and consistent way, but it's a titration nonetheless. And the idea is the moles of acid equals the moles of base, or moles of base equals moles of acid at the equivalence points. So a titration of a 10 milliliter sample of hydrochloric acid requires 12.54 milliliters of a 0.1 molar solution. So how do we do this? So you can use, there's 2 ways to do it. You can use the, I guess I'll do the long way. Why not? So dimensional analysis, 12.54 milliliters of sodium hydroxide. So liter, 1,000 milliliters. And then we have 0.1 mole NaOH per liter. NaOH. And now we have mole HCl per mole NaOH, because there's a 1-to-1 molar ratio there. And then we have, so we divide by 10. So we have 10 milliliters HCl, so then we have 1,000 milliliters HCl, liter HCl. And then we'll be left with moles per liter. Yeah, that'll work. So if you look at the units, milliliters cancel, liters cancel there, moles cancel, milliliters cancel there, and that means we would have 12.54 times 0.1 divided by 10. So 12.54 times 0.1 divided by 10. And 0.1254. How many sig figs we have? 3. So 0.125 equals 0.125 molar HCl. Okay, so that's one way to do it. The other one, the way you can do it is C1V1 equals C2V2, and you could have 0.1 times 12.54 equals unknown 10 milliliters, and then divided by 10, and get your unknown, which is the same way as doing that. But I want to do the dimensional analysis to show you how you can be attacking these problems. I'd probably do the molarity 1, the concentration 1, volume 1, plus concentration 2, volume 2. But either way will work. So let's see here. How many milliliters of 1 molar sodium hydroxide solution are you to neutralize 10 milliliters of 0.1 of 1 molar sulfuric. This is kind of a trick question because you think, oh, if it's the same concentration, I need the same volume. The problem is the sulfuric is diprotic. You need twice as much, so the answer here is actually 20. Okay, so let's talk about different types of reactions. We talked about precipitation reactions, acid-base neutralization reactions. So what else can we do? We can generate gases. So for instance, hydrochloric acid plus sodium cyanide makes sodium chloride and hydrogen cyanide gas. And I've smelled hydrogen cyanide gas, and I can tell you it smells wonderful. It smells like roasted almonds. It's a really nice smell. Cyanide, though, one thing with cyanide, you just smell it and you get used to it really fast. So I smelled roasted almonds, and then the smell disappeared. I'm like, oh, that's a chemistry science for uh-oh, and which means I just smelled cyanide. I had the curse of the idiot lab partner in organic chemistry, and my lab partner mixed two things that needed not to be mixed and generated cyanide. Fortunately, the nice thing about, well, the first thing I did is I went to an instructor, I'm like, I just smelled cyanide. And he's like, you're fine. And one thing about cyanide is it kills you fast. If you can get up and say, I think I have cyanide poisoning, you are probably fine. So let's say you're out somewhere and you smell roasted almonds, and almonds actually get their flavoring from cyanide. So when you taste almonds, you're tasting cyanide. But it's a very slight concentration. So let's say you're out in a Christmas market in Chicago and you smell roasted almonds, and you're like, oh, cyanide, I'm going to die. And in front of you is, candied nut maker. You're probably okay. If you are in a refinery area, has a bunch of tanks, and then you smell roasted almonds in the middle of these metal tanks, and then the roasted almond smells like, wow, that's a really nice smell of roasted almonds, and then it stops. I recommend you turn around and you run, and as you're running, start praying to whatever deity you believe in, because if you might be getting a toxic dose. So, but cyanide, that's one thing. One of the things you can do. This is what they do for gas chambers. They put sodium cyanide and hydrochloric acid, and then that forms cyanide gas. And that's how some people are executed. Okay, so we can form other gas evolution reactions, sulfides. So hydrogen sulfide. So potassium sulfide, if you can see this. So acid plus potassium sulfide forms hydrogen sulfide. Hydrogen sulfide smells like rotten eggs. It's a horrible, horrible smell. Carbon dioxide, what is this calling it? Carbonates and bicarbonates. Okay. So carbonate or bicarbonate. So the word bi in chemistry class means an extra hydrogen. So carbonate is CO3 and bicarbonate is hydrogen HCO3. So sodium carbonate, also known as washing soda. Washing soda is Na2CO3. Then there's sodium bicarbonate, also known as baking soda. So baking soda is sodium bicarbonate. It is the bicarbonate of soda. Sometimes you see that in old packaging. Okay, but either way, you throw acid into carbonates or bicarbonates, carbon dioxide is produced. Sulfites and bisulfites, you mix those with acid and it forms sulfur dioxide. Gives me a headache whenever we do this experiment in the lab. And ammonium, I should say, they make ammonia, NH3. So ammonium chloride plus potassium hydroxide will make ammonium vapor. And that stuff hits you hard. Okay, so let's talk about the next type of reaction. and it's oxidation reduction. And pay attention to this. We cover it in this chapter, but it'll come again to haunt you when we get to electrochemistry and then Gen Chem 2. But oxidation reduction, so oxidation, couple definitions: adding oxygen, removing hydrogen, and the most general term for oxidation is loss of electrons. So if oxygen is being added on one side of the equation, that means oxygen is taken away from the other side of the equation. So reduction is the opposite of oxidation. Reduction means loss of oxygen or gain of hydrogen, and most generally it means gaining of electrons. So what? Well, oxygen is the most common oxidizer. It's the one that grabs electrons. It's the oxidizing agent. It grabs the electrons. The reduction, so if oxygen is grabbing electrons from something, well, it's being reduced. It's getting electrons added to it. The most common reducing agent are fuels. So oxygen is the most common oxidizing agent. The most common reducing agent is fuels. So oxidation reduction, they happen together. So we call the reactions redox. I guess that sounds better than ox-red. So we call them oxidation reduction or redox reactions. So we're going to learn a couple ways to describe where electrons are. Oxidation states is one way of describing where electrons are. And there are some rules for it, and it's hierarchical. So rule number 1, any free element oxidation is 0. Rule number 2, a monatomic ion oxidation state equals its charge. So monatomic means one atom. And the sum of oxidation states for all atoms is a neutral, molecular unit is 0, or for a polyatomic ion equals the charge. So group 1A metals always have an oxidation state of +1, so alkali metals, alkaline earths, group 2A, always have +2. And then for other things, we have a chart as shown here, where fluorine is -1, which is more important than hydrogen being +1, which is more important than oxygen being -2. 7A, the halogens tend to be -1. The sulfur, the oxygen family tend to be -2. Nitrogen family, -3, the columns in the periodic table. Okay, so let's use these rules to assign oxidation states. So chlorine. Chlorine is a free element. Its oxidation state is 0. Sodium, next one, B, sodium +1. This means that it's a monatomic ion. This oxidation is +1. Potassium fluoride. So we go down the list. The sum of a neutral formula molecule is 0. So we know that potassium plus fluorine, so potassium plus fluorine equals 0. And then we keep on going down. And rule number 4, group 1A has to be +1. So +1 for potassium, plus, that means fluorine needs to be -1 equals 0. So this is +1, -1. So carbon dioxide, same thing, go down to rule number 3. 0 is equal to carbon's oxidation state plus 2 times, I'm putting OX for oxygen. And going down, we get to rule number 5. You have a chart, oxygen tends to be -2. So 0 is equal to carbon plus 2 times -2. 4 equals oxidation state for carbon. So we have 4, and then we have -2 for the oxygen. So next one over, sulfate. Same rule, except for we have the charge, this -2. I'll zoom in for you. -2 is equal to sulfur's oxidation state plus 4 times oxygen's oxidation state. -2 is equal to sulfur plus 4 times -2. And then, so I'll do the whole 2 is equal to sulfur plus a -8. 6 is sulfur. Oh, 6 plus 6. That's true. 6 is sulfur. So we have +6, and we have -2 for oxygen. Now, this next one, last one, potassium peroxide. We're going to have 0 is equal to 2 times potassium plus 2 times oxygen. as demonstrated. And if you look at the chart, potassium has to be +1, so look here. Rule number 4, which is above rule number 5, rule number 4 says that alkalis are +1, 0 is equal to 2 times 1 plus 2 times our unknown. And that means -2 equals to 2 oxygen, -1 is equal to oxygen's oxidation state. So this is +1, -1. You're like, wait a second, oxygen tends to be -2. Well, right there, it tends to be. So it doesn't mean it has to be. So oxygen can be -1. And when oxygen is -1, that's known as a peroxide. So another thing, oxidation states can be fractional. You can have a -1/2. That's known as a superoxide. Peroxides and superoxides, especially superoxides, tend to be very, very explosive. So we're going to have the easier ones. But hydrogen peroxide, oxygen is -1 in hydrogen peroxide. Okay, so let's look at this next example. What is the oxidation state in potassium dichromate? So that means 0 is equal to 2 times potassiums plus 2 times chromiums plus 7 times oxygens, like so. So potassium tends to be +1, oxygen tends to be -2. So put those in there. 0 is equal to 2 times +1 plus 2 times chromium plus 7 times -2. 7 times -2 is -14 plus 2. That means that 2 chromium equals 12, which means chromium equals 6. So this is +1 plus 6 -2. And chromium in the +6 state is pretty nasty. So it is a skin irritant, and it also is a carcinogen. So dichromate is very bad. Although you can get some real pretty yellows out of it. Like the Minions and Despicable Me, they're probably swimming in potassium dichromate because that's what the color is basically. It's like a minion yellow. So it's a very, very bright yellow with that one. You can patina art with that. So if you see a very bright yellow bronze statue of a minion, I probably wouldn't touch it. So, although at this day and age, I guess they could have painted it. If you saw an ancient statue, don't touch it. So, and I mentioned chromium. Chromium in the +3 state is totally fine. It's the +6 state. That's the bad stuff. So the oxidation states do matter. Okay, so what is the oxidation number for manganese and potassium permanganate? We can do this one again. 0 is equal to potassiums plus manganese plus 4 times oxygens. Potassium tends to be +1 plus our unknown plus 4 times -2. 4 times -2 is -8 plus 1 is equal to +7. So manganese is +7 oxidation state in potassium permanganate. It's an angry manganese. So what else is the oxidation state yielding to? It's telling you where electrons are. So it's generally telling you that manganese has 7 fewer electrons, which means it's very electron poor, which means it's gonna gobble some up. And potassium permanganate is really good at grabbing electrons. So because it's straining that magnesium. Okay, so let's move on and talk about some redox reactions here. So magnesium plus 2 waters makes magnesium hydroxide and hydrogen gas. So what is being oxidized? What is being doing? Well, let's talk about the oxidation state. Magnesium is a native metal. It's a native element. It's got a state of 0. Water, hydrogen is going to be +1, oxygen is going to be -2. Magnesium hydroxide, magnesium is +2, oxygen is -2, hydrogen is +1. and hydrogen gas native element is 0. So what's going on in this reaction? In this reaction, magnesium is giving up electrons to the hydrogen and water, and then hydrogen gas. Hydrogen is absorbing electrons and forming hydrogen gas. So magnesium is oxidized, it's lost electrons. Hydrogen is being reduced, it's gaining gaining electrons. So what is causing what? So magnesium is being oxidized, but it's causing, by giving up its electrons, it's causing reduction. So the species that is oxidized is the reducing agent, and then the species that is being reduced is the oxidizing agent. So it's like James Bond having the license to kill. He's a killing agent. So he doesn't die, he delivers the killing. He doesn't be killed himself. So the reducing agent delivers the reduction, and the oxidizing agent delivers the oxidation, but they themselves are doing the opposite. So, all right, look at this reaction here. Glucose plus oxygen forms water and carbon dioxide, unbalanced. What is the reducing agent? Well, the first thing you can kick out is carbon dioxide and water. They're on the right side of the equation. It's the reactants. The reactants are the left side of the equation, are the ones that have to be the oxidizing and reducing agent. And you can do this a couple ways. You can look at the oxidation states. Carbon is 0, and it's +4 here. So carbon is the one being oxidized. So since being oxidized, it's the reducing agent. So that's the reducing agent. And what's another definition of oxidation? If you didn't want to do that, the adding of oxygen, you are literally adding oxygen to it. You can't get more literal than that when you're adding oxygen. The other thing is, if you remember what I said, that the most common reducing agents are fuels, and sugar is a fuel, and the most common oxidizing agent is oxygen. So if oxygen is there and it's the oxidizing agent, guess what the reducing agent is? So, but there are several ways you can solve that problem. Hopefully that all made sense. And you are now, this will come again later. We're not going to talk about it too much now, but this will become important later in the second semester. So don't dump your brains on this just yet. And if you hadn't noticed in chemistry, everything comes back to haunt you. You'll see this again, don't worry.